In today's episode, we're diving deep into the final frontier of space. Is colonizing Mars just science fiction, or could Elon Musk actually make it a reality? And what about the wild conspiracy theories that surround NASA, space exploration, and even our own planet? Are they just myths, or is there something more? Today, I've got Dr. Richard Olenick on the show, a leading physicist and astronomer, here to help us navigate fact from fiction. Hope you enjoy. So speaking of planets millions and millions of miles away, Elon Musk is fascinated with Mars, and so am I. Is colonizing Mars something he can really accomplish?
Yeah, I think so. Especially, I think rovers are now showing that there's underground water on Mars. So that's going to be the secret, is to find enough water, because we can't transport it there. It'd be too heavy of a load. So as long as there's going to be water that we can extract from underground, then I think we could have some kind of sustainable living there. The only problem will be that the radiation levels are going to be higher because the atmosphere is so thin. So probably we would have to construct, probably the first time we would live in caves or some places that we could find that are sheltered by ground. And then we'd have to do 3D printing and make structures out of it. We're using Martian soil and make it thick enough then to block out some of the cosmic rays that are coming in there. But it should be okay. I don't know if you ever saw the movie Total Recall.
Yeah, for sure.
Okay, remember they're on Mars.
Yeah.
And they're actually, I think, living at Velas Marineris, which is this huge canyon, which is a rift canyon. It's not a water canyon like the Grand Canyon. It's where the surface got pulled apart, and it's much, much deeper than the Grand Canyon and much, much wider as well. I think that they were showing people living there, and that made more sense because there would be nooks and maybe caves around there that people could have lived in. And the other interesting thing in the movie was that there were the humans that had been living there were Martians, but then they had the from the radiation, they started having mutations, and you got to see them. And that's quite likely would happen if we didn't have enough shelter for them.
So the radiation is the radiation from the sun that's coming?
It's partially the sun. It's also just from outer space, too. We get
And the fact that there's no atmosphere, is that right?
Little atmosphere,
Or little atmosphere, right?
Yeah.
So, so it wouldn't. It's not just light that's hitting you from the sun, but it could be just emanating energy that's radiating, and so the structures would be enough to, or caves would be enough to prevent.
Yeah, block it.
Yeah,
it would block it, and we use that on Earth. By the way, we have a lot of experiments in old abandoned mines where we want to look for some cosmic rays that can only penetrate really through all that dirt, and all the other ones get blocked out. And so there's been now there's some searches for cold dark matter that are done in these ancient mines. Very
cool. What about being able to breathe, create the oxygen necessary?
Yeah, breathing. You can sustain yourself breathing the atmosphere of Mars because there's too much carbon. It's mostly carbon dioxide. It's like 97%, and so you would have to be producing oxygen. So most likely we'd have to have a way of breaking down the CO2 into an oxygen component and then storing that and breathing. And then once you have facilities, of course, you can fill them like we do with air conditioning kind of units where the whole place is going to be not only insulated, but also pressurized to keep that atmosphere in there.
Okay, so that takes care of oxygen. What about energy? What would be the most?
Oh, solar.
Solar?
We've gotten pretty good with solar now. So I think solar could easily power everything they really need.
Even heavy machinery and everything like that to do the building?
I think it can. I think it can. It's really advanced. I, by the way, put in solar in my house in North Carolina last year.
Oh, cool.
And I love it.
That's great.
And I even and I have a Tesla battery backup to store. I use no electricity.
No way.
Because of the batteries I run at night.
So it's paid. I mean, it was an investment on the front end.
Yeah.
But it's paid for itself essentially.
And I'm selling electricity to the power company at the rate they charge me. So I'm making money. They only pay you once a year, but I'm expecting probably maybe a couple $1,000s back from them.
That's great. That's like not that case the other way around. So how long did that investment pay off for itself? Like how long before it paid off for itself?
Well, it hasn't yet paid off.
Or how long will? Yeah.
Yeah. So at what it's going now, it's really about 10 years. I think it's.
Yeah, I mean that's not bad though. And I mean, if they're built to last longer than 10 years, obviously.
Yeah, they are.
Yeah.
And so I tell my students now, I said, when you get a house and if you've got a good job, you got to look into putting in solar if you want to. Because I said in 10 years, it's going to be paid off. And, you make that investment.
I heard there was also tax deductions for them.
Yeah, that was the big surprise. I kind of knew there was. And then when I got my accountant did the taxes and I got it back, I'm like, $10,000 back. I thought I was going to have to pay. And
right.
That helped me.
That's great. Yeah, so. For sure. That's like definitely a pro. So solar energy, and you mentioned water. So how would we get, would it be as simple as just drilling down there and getting ice and melting it? Or what would that look like? That's
the hope. And actually, it should be water when we go farther down. We could also be at the polar ice caps, which have lots of water there. But I think everyone now is agreeing that there used to be a huge ocean covering most of Mars. And the water evaporated from Mars because Mars, being smaller than the Earth, cooled off faster. And so the internal heat was gone, and that internal heat allows the inner core of the planet to be molten, and it also rotates. It's ions in there, so that creates a global magnetic field, and that global magnetic field, like on Earth, shields a planet from the effects of the sun and some of the cosmic rays as well, but mostly from the sun. So without that, you're bombarded more and more, and over billions of years, the atmosphere just kind of got knocked away little by little by these particles and went off into space. As the atmosphere was thinner, it created lower pressure. That meant the water would evaporate up, and then it got knocked off into space. So there should be some underneath yet, and I'm confident there is. And so it'd be drilling.
Right, drilling. And getting it in whatever, filtering it through whatever means to be able to make it drinkable or usable for whatever purposes.
Yeah.
Okay, so those are like the kind of practical approaches as to the how. Let's talk about the why. So we've got, if you can, I don't know what the statistic is exactly, but you might know. But I've heard if you condense the entire population to a certain like square area that's livable, you'd have tons of space still left on Earth. And we still do have tons of space left on Earth. Even the most uninhabitable, I'm assuming the most uninhabitable places on Earth are probably more habitable than any place on Mars for the most part.
Yeah.
Yeah, generally speaking. So why?
Why go to Mars?
Why go to Mars, and why does he have the obsession with Mars like now? I guess maybe it's a legacy that he wants to accomplish, but what would be the why?
Okay, I think the why is going to be a practical reason, and part of that is mining. The first why is because it's there. It's something reachable. It's much more hospitable than Venus is. We're not going to go and try to live on Venus. And then the outer planets are all gaseous. There's no surface, so we can't go there. Although some of the moons might be a possibility, but it's going to be really cold and frozen out there. So Mars seems to be the best candidate for us to set up settlements and see, because I actually think Musk believes it's our destiny to keep going out into space and go to other planets. I think this is our first step. But there's the business end of it also. I am positive he wants to mine asteroids. An asteroid belt, is outside of Mars. And so you have a base at Mars, and from there you could start sending automated robotic satellites to mine asteroids. And because the asteroids will contain, like there's one that contains, like thousands of times the amount of gold that we think exists in our world.
Oh, wow.
And just in one asteroid. So there's a lot of precious metals, but more importantly, probably some of these rare earth things that we're using, like europium or what's
Making
another
chips.
palladium for chips
Yeah.
and for pixels, colors in displays. So I think that's if I were to talk to him, I'd ask him that.
It's like the movie Avatar. So many movies have been made into this story where you're going off to this distant planet just to go mine this, special element or rock, this ore to get the financial benefit, which makes sense.
Yeah.
But it's crazy that the science fiction, those ideas are slowly starting to become a reality.
Yeah, and I've been thinking about that lately because it seems so many science fiction writers were prescient knowing that this is what we're going to be doing, and even problems we encounter and means that we use to get there. I was like, wow, they're prophets in a sense. And I'm like, how did they do that? It's like, is that their genius or their creativity? But it's so really grounded in what's becoming our real science now.
Right, yeah. And saying that, talking about that our future lies in colonizing the planets, how, do you agree with that statement first? Do you think that's like the next, I guess, step? Like, I've heard a few different physicists talk about like, I forget how they categorize it. It's like the stages of evolution and where we are in our current state. And
there's the stages, if you wanted, of a civilization. There's class 1, 2, 3, and we're in like 0.7. 1 is where you access all the resources of your planet for energy. So we're getting there. We've used fossil fuels. We're using solar more. We use wind. We use waves. So we're about 0.7. A category 2 is one that can harness the energy of the sun, all of the sun. So all the energy of the sun, not just the little part on Earth, but all of it.
How would that look on a practical bit? Help me wrap my head around that one.
Okay. The first person who entertained this notion was Freeman Dyson, a theoretical physicist. And he said, well, if a civilization were to construct a device that totally encased the star and absorbed all of that light energy and particles coming from the sun and could convert it into energy, then they would have unlimited energy to do anything they wanted. So it was then coined Dyson sphere, this object around the star. So he imagined it as a sphere centered on it. He realized right after he came up with the idea that the sphere will not be stable. And so what's going to happen is it's going to go crashing into the sun and things like this. So you have to, more realistically is something like we have on Earth already. We have networks of satellites orbiting in what we're going some are in the geocentric orbits like your dish TV, but most of them are going to be in low Earth orbits. And so we have a network goes around. We have, Skylink from Musk. And so I think setting up large energy, basically solar arrays to capture energy and having them in orbit would be a more feasible way of constructing a Dyson sphere.
Outside the sun and the Earth?
Probably outside our orbit
Okay.
or inside our orbit, probably. Well, then we won't be outside our orbit. We're still inside of it.
Right.
Yeah. And that would be one more practical way of harnessing that energy.
And how would the energy be transferred wirelessly? How would that kind of work?
Probably microwaves right now. I mean, there have been proposals to do that now with satellites that are basically just big solar arrays. They absorb energy and they just beam it down to the Earth.
Oh, whoa.
Okay. Now
they're frying things on the way down.
Yeah, I'd hate to be a bird that
yeah, gets hit by one of those things.
Yeah. But if it's in geosynchronous orbit, that would mean it's over 1 point, and so that's a little better. But still, there's going to be like this no travel zone for any satellite or anything that would come down. So still trying to work that out, but it would have to be beamed through most likely microwaves.
So that would be a stage 2?
Yeah, that would be a stage 2 population. And then I'd like to add that I was excited this summer because a paper came out and they did data mining of stars with planets that have been discovered by, I think, both Kepler and TESS satellites. And so there's about 5,000. And then they looked at basically the thermal signature of the star, which would mean most stars emit more energy at shorter wavelengths when they're hotter. So they're called thermal radiation curves, and they're used in astronomy a lot. And so, but all these curves always, as you get to longer wavelengths, they taper down. Mm-hmm. But they found 53 stars initially that went back up, and that's an anomaly. It shouldn't do that. And they refined it further, and they were left with 7. And so they said, what could this be? And one of the suggestions was maybe it's a Dyson sphere.
Oh, wow. So there's
something other, because that then absorbing energy, it would also be re-emitting some thermal energy at longer wavelengths, and a lot. And so that's why they thought they were seeing it. So I was quite excited because a few years ago, gosh, now it's got to be about 5 years ago, a student was looking at data from the Kepler satellite, and we were looking for exoplanets, and we found some anomalous signatures on it. So then a colleague of mine in Florida started analyzing it, and we concluded there were chunks, big chunks going around this binary system, actually, of 2 stars. So when I saw this paper on Dyson sphere, I sent it to her and I said, Michelle, maybe we found part of Dyson spheres going around there. She didn't comment back on that, but I'll be seeing her in a couple of weeks, and I'm going to push that issue because who knows? But so
that would mean there's another stage 2 civilization out there.
That would be it. So that's what's so exciting.
How far away is that?
The star we were looking at isn't that far. I think it's only about 1,000 light years. So relatively close.
Relatively close.
Yeah, relatively. So anyway, then stage 3 civilization is one that harnesses the energy of the entire galaxy. And that's just unfathomable. I mean, I don't know what you would do with all that energy.
Right.
I tell my students that at that state, the civilization should be able to probably transcend being physical, and second of all, be able to create matter at will, having devices that can take all that energy and create that. Also travel through space by creating wormholes and all these things we'd love to do, but we know we don't have enough energy.
When you say creating matter at will, would that mean creating any object whatsoever?
Yeah, that's what I think.
Essentially,
any object. Yeah. Okay. Going back to science fiction writers. One of my favorite movies as a kid was Forbidden Planet. And Forbidden Planet is the Tempest set in space. And I think it was in that movie that Robbie the robot was introduced. That was a funny robot that would go danger.
Will Robinson.
Will Robinson was in there, but it was kind of introduced in that movie, which I think was 1955 or something. Anyway, there's a humans go to investigate where a spaceship had crashed, and they find there's only one survivor, and this happened, maybe 20 years earlier, and one, his daughter now. And then, so he talks to them and says, well, it turns out, to cut to the real plot, that there was a civilization there called the Kral, and this guy, who was a physicist, was able to tap into their energy reserves, and they had devices where they could literally create matter at will, and that's what they were used to. And they showed some of their, I can't say machines, but devices to create energy underground. It's just like miles and miles as far as you can't even see the end of it going. And then they could harness all that energy like that. And the thing that happened, though, was the Kral had forgotten that they had evolved from lower creatures. And so there was not only the ego, there was the libido, which was kind of their ancient side. And so that got powered by these machines and ended up destroying them.
Oh, wow.
Kind of like what could happen maybe with AI taking over and controlling robots and turning on us.
Right.
So it was not a robot, it was really part of themselves that turned on them.
That's definitely got more of a message there than deeper meaning than robots taking over.
Yeah. So I watch that movie every year because I just love it.
Do you think part of also, are there any other, so there's 3 stages?
Yeah, that was 3. Some people are putting a stage 4 now. I can't imagine.
What would be beyond that, right?
Well, you're going to cluster galaxies.
Right. As far as like being able to read and communicate telepathically, that would be stage 3 most likely as well. Just anything.
Yeah. Probably even stage 2.
Right.
I think stage 2. We're talking about the sun there's a lot of energy coming out of the sun. We just get such a little portion on Earth. So I think maybe even a stage 2 could do that.
Where consciousness itself would be removed from the physical plane, possibly as well.
Yeah. And that's what I think physicists and computer scientists are looking at, which scares me.
I read, speaking of consciousness, there was I don't know if you've read this article. Somebody used quantum mechanics as a scientist or quantum engineering to say that human consciousness, life and death is a fabrication. Are you familiar with this article?
Yeah, there's a lot like that. That's kind of it's I'm not a big fan of it. That's why I'm hesitating.
I can tell your hesitancy. It's far-fetched, I guess you'd say, or where's your hesitancy?
I'll look at the sort of a aspect of it, and that is that some physicists say that time doesn't exist; it's all an illusion.
Right.
And I know what they're saying, but when the average person hears it, they think, "No, there's no time. This world's all an illusion." No, there's something more to time. And you know music. We live in the present, but we have a memory of the past, and we also can project the future. So if you're listening to Bach, you can really just about anticipate what the next notes are going to be from what you've heard. And so even though you're in that present, you still have the memory of the past, and you can see that there's a future. And I think that to me says, nope, something's real.
Yeah, and concepts like that just are so hard to even wrap our heads around, just because it's just so beyond our capability of understanding. So,
on the other hand, things, the perception of time or the physical measurement of time, that can change, and that's a very real thing, especially the measurement of time, like time dilation and.
Yeah, for me, my sense of time, and I know this is the case for a lot of people as they get older, but my sense of time has completely felt like it's gone out of whack as I've gotten older. But also just recently, just in the last few years, it's felt like time is going by. It's really hard for me to gauge sometimes, like if time's going by very fast or very slow. So I'm just like, well, was that yesterday or was that like 2 weeks ago?
Yeah,
maybe that's just me getting old.
No, I actually wonder, because I experienced the same thing. Most of the time I think, oh, everything's going so fast. And I think that's because the older you are, the more memories you have. And so you have more to store. And, it's not like being in grade school just waiting for class to get over and nothing to do. You don't have many memories then. And so I think, or experiences, I should say, because you may not have memories of everything, but you've had so many experiences. But the times when it goes slow, which I experience too, that then really amazes me. But I always know it's usually when I'm deep into thought, either in my work or reading a book or something. And then I've literally been amazed where I feel, wow, I've been reading for 2 hours and it's been 20 minutes.
Right.
And it's just like, wow, it's just interesting that it's changed. That it can go back and forth now.
Yeah.
And I wonder if COVID had something to do with that.
Yeah. I'm going to be having a medium on the podcast, and there's in the astrology field and mysticism field. And, again, it's very foreign to me, so I have to do a lot more research, but she was saying something about this time period, us coming to the end of a certain period having to do with every 27 years because of Saturn, ascending, saying that there is a direct shift in time and perception of time itself is changing. So I'm going to get more answers on that side of it, but it's interesting hearing it from your perspective as well. We're talking about colonizing other planets for just for us to head out there. But let's just say we had like an Armageddon style event where an asteroid was headed to the Earth. Like, let's just say we found out it was discovered, tomorrow. What would happen? How I wouldn't say how we would prepare, but what would happen if we knew that there was an asteroid on a collision course with Earth, depending on the size?
Okay, I'd like to preface it with one thing, and that is we've gotten very good at observing and predicting asteroids that could hit the Earth. And lately, NASA has been very happy because they predicted when and where some large chunks, so there's still asteroids, would hit. One was, I think, a few weeks ago in the Philippines. And so being able, and they're small, I think that one was like a really big boulder, but that's small. And if we can detect and give its path, that means larger ones we will know about ahead of time. So after comet Shoemaker-Levy smashed into Jupiter in 1994, 95, we got really scared because we know what could happen here. And because that was like, I don't know how many millions of H-bombs going off at once.
Right.
And
worse than the one that hit the dinosaurs?
Yeah. And
or that we think killed the dinosaurs off the Gulf of Mexico?
Yeah. So we're like, okay, how can we, A, know if this is going to happen, and B, do something about it? So one is, if we detect the asteroid early enough, there are some fairly easy means, but it means we have to have a rocket, a probe we can send out to it fairly quick. And one is to smash into it, and we actually did that with a moon of another asteroid, and we found out we were able to knock it off course quite a way, and so we were more than we thought it was going to go. So I think that was a success there. And if it's far away, you only need to knock it off course just a little bit to miss the Earth.
Yeah.
Another idea is a tractor beam, like you have in Star Trek. And basically it just takes the satellite and it hovers near it, but it's moving away a little, and it's kind of, even though it's a really small force, if there's enough time, it can deflect it a little bit to miss the Earth.
The gravitational force?
Yeah.
On it? Oh, okay.
And another means is you use paintballs. You put white paint on one side, and it's actually the pressure of light that can deflect it.
Oh, wow.
So we've got, then you could do the Armageddon or the deep impact idea of launching nukes and blowing it up, but that's not the preferred one because you still get chunks,
right,
and stuff. So I feel that we are not in control, but we're much more aware of the situation and what we can do. And the last thing is the number of asteroids that are large enough, like size of Mount Everest was about the one that killed the dinosaurs, that could destroy all life on Earth. Those happen maybe once every 100 million years. Mm-hmm. And so, yeah, it's been 65 million years, so we got a ways to go. But that's just an average. But we think all of the large asteroids have collided or they're in stable orbits now. But that having been said, there's the Kuiper Belt and then the Oort cloud, which the Kuiper Belt is where, say, Neptune is, beyond Neptune. And we found Pluto, for example, is called a trans-Neptunian object as well because it's out there. And there's several, some of which are larger than Pluto out there. So we know that there are icy worlds out there, some large ones. And then the farther out, much, much farther out, is this cloud of trillions of comets orbiting the sun. All it takes is a star to come close and knock those out of orbit. Right. And then that disturbs them. They're going to come closer to the sun because they are orbiting the sun. And then that presents new dangers. So even though it was like, okay, the dinosaurs happened 65 million years ago due to a cometary impact, we can't say, we're totally clear forever because stars do come close to us, relatively close.
I'm amazed that, most scientists, including yourself, can confidently say that we can kind of see everything that could become. The Earth is huge, to be able to like, how are we able to see so much of space to confidently say that we're safe from a giant meteor hitting us?
Well, the giant ones are easy because we have Pan-STARRS is one project that just searches. And all you do is you take pictures of the sky. They try to do the whole Pan-STARRS, I believe, does the whole sky. And then you do it the next night. And you look for things that are moving from one day to the next, or usually about from one day to another. Mm-hmm. And then if only about 5 points, you can actually predict the orbit from that. And then we know what it's going to do. And NASA, actually, you can look it up. They have what are called potentially hazardous asteroids, PHAs, mm-hmm. or any NEOs, near-Earth objects, and they monitor them. And so I like occasionally going to the website and looking what's been discovered, but most of them are definitely not crossing our orbit, and we're safe.
That's good. Are there? I wanted to also, or we'll come back. There's a couple questions I have with that, but I want to talk about the Big Bang because we talked about that last time. And I didn't ask this question. I wish I would have. Are there any other theories that alternative to the Big Bang that in the scientific community? Is that the
okay? Well, we have something called the Standard Model, which is going to describe how the universe evolved from the Big Bang. And that's pretty solid. There's the problem with dark matter yet, but I think the beginnings is pretty set, and it took less than 3 minutes for the stage to be set for the universe to evolve to where it is today. But then it's like, okay, what was the source of the Big Bang? What happened there? And that's when you move into other ideas like string theory. And string theory basically states that we have 11 dimensions.
I wanted to talk about that too.
And so that's hard. I can do 9. I can do 10.
When you say hard, you mean like wrap your mind, understand? Yeah.
But it's the 10 are kind of easy. We have 3, and then you have time. Okay, so we're used to 4 dimensions, and that was all of Einstein's work. Is 4-dimensional universe, and space and time are connected. In string theory, you would have each of our physical dimension of length, width, depth is going to be 3 dimensions. And that you can easily see, because if you look at, say this rod, you can see it exists in 3 dimensions, right? If we were to look at it far, far away, you'd see only a line. Mm-hmm. And so for each one of our dimensions, they're not 1, it's actually 3 in there, kind of wrapped around. So length this way really has a length that way, but it also has something that goes around this way and then goes around this way too. So there's each of our 3 dimensions has 3, so that makes 9. And then you add time, you got 10. And then you add one more that everything's moving in. And we are then in the 10 dimensions. We're on something called a membrane, or a brane, B-R-A-N-E for short. Mm-hmm. And those are moving around in this other dimension, and they can occasionally collide. The collision was the Big Bang then. And then that created in this one membrane a release of energy and evolved into our universe.
Wow. I want to keep talking about the string theory. Is string theory related in any way to like alternate dimensions?
Well, yes, because it does have these additional dimensions.
Right.
Yes. And they would,
but I mean, in the sense of like, or like in the movies where it's like there's like 5 versions of me, and or
so
infinite, multiverse type of thing.
Yeah. That's a quantum mechanical idea.
Oh, okay.
Multiverse. These dimensions there exist only on a really, really small scale, not in our present size.
I see. Okay.
So, multiverse. I'm not for sure on this, so don't quote me, but I think the idea originally came from a guy named Everett, and he was a student of John Wheeler, mm-hmm. and it has to do with the biggest mystery in science, and that is, what is quantum mechanics and how does it work? Mm. And so quantum mechanics is the most successful theory we know. It can predict things to 9 decimal places, and you measure it, it's there. So, excuse me, there's really something to it. But as the Nobel laureate Richard Feynman said, nobody understands it. So there are 3 sort of camps of interpreting how this works. One is that there are hidden connections between our mind and the physical world.
This is how you're explaining quantum mechanics, or
quantum mechanics.
Because I've never understood it in the first place. So
well, and I'll hopefully tell you a little bit how we understand it. But there's this theory, it's called hidden variables, and so somehow our minds were in sync with these hidden variables, and that's how we're able to then get a measurement out of something. But the universe in that case is pretty much like Newton's, very mechanistic. And you have cause and effect just like normal. But we just don't know everything is kind of what it's saying. That's pretty much been disproven by something called Bell's theorem. Another way is what Everett had, and that was that when you do a measurement on something, so we always go to measurement because quantum theory is a theory of how to do measurements, really. And when we measure something, you have to interact. And so the example would be if I put out my palm and I said, can you touch my palm without my palm touching you? You can't do it, right? You have to interact. And same thing in the quantum world. We have to interact in a measurement. And measurements change the system. They cast the system, we say, into different states. So anyway, but measurement acts on the system, and it should act back on you. And so Everett said, so if it acts back on me, then I am a subject like the kind of stuff I'm measuring. So we're going to go to Schrödinger's cat. And Schrödinger said, okay, if you take a cat, put it in a box, and have a vial of prussic acid and a hammer poised above it, and the hammer can fall by a trigger from a radioactive nucleus that has a chance of emitting radiation so that in an hour, there's a 50-50 chance to trigger the hammer. Okay, so it's just to try to get some probability in there. So you have this cat, has a 50-50 chance to be dead or alive in an hour. And then you say, you cover the box up, you put it in your corner of your room, and you say in an hour, without looking, is the cat dead or alive? And quantum mechanics has to say it's both dead and alive, because you do not know until you take a measurement. The measurement will be the act of taking the cover off and seeing it and saying, oh, it's alive or it's dead. But quantum mechanics says it was both dead and alive. What happened to that part when you see it's alive? What happened to the part, the wave function that said it was dead? Well, it becomes a ghost kind of thing. So in this idea of it, that hidden variables said, we control what the outcome of the cat, really. And it's our minds interacting that when we open it, it's going to be alive, for example. And as I said, that's been discounted. Everett's, which I thought was really creative, said, you look at the cat, and when you open it up and the cat's alive, the universe splits and you split. So
there's a scenario where the cat's dead and a scenario where the cat's alive.
So you split to two universes.
Okay.
So we start to get a multi-universe. So anytime a decision, a measurement, anything is made, the universe splits, which means there's
infinite
Google number of these, which is kind of crazy too.
Right.
So people don't like it, that interpretation for, I'd say, that reason.
You say people, you mean the scientific community?
Scientists. Okay. The kind of people
for
that
you,
hang
that's
out
just,
with.
for you, it's just people.
But the interesting thing about it is that we are subject, just like the cat would be a subject. So it's this, we have to have a consequence of doing a measurement. So, but the standard interpretation was called the Copenhagen, and that got ironed out by a couple of conferences in Europe with the leading physicists of the time. I mean, it's just, you had Bohr and Heisenberg and Madame Curie and all the giants in the pantheon of physics were there. It's just, and that doesn't happen anymore, by the way. Right. It's just amazing how they put the framework. And the framework got to be as, well, we can't say the outcome for one cat. We have to do, say, 100 of these cats. And then after an hour, 50 of them will be alive, 50 will be dead. It's all probability. Okay. So that is the standard, and it works, and we do that. And it says don't ask questions, but physicists like to ask questions, especially ones that push the physics towards metaphysics. So we want to know why. I mean, there's a why there yet too.
Right.
And we're approaching it because the other thing then that we've discovered is in quantum entanglement. And that's going to be where particles can be, when they're created, I like to give an example. There's one particle, a neutral pi meson. And when it decays, it emits light. But it has to emit two particles of light in opposite directions because momentum has to be conserved. So if it's at rest, they go off in opposite directions. But now the idea is light has another characteristic. It's called spin, but you can think of a direction that some entity of it's pointing. And we also know that has to be conserved. So if you measure that spin of one of the particles of light, a photon, and compare it to the other one, they always have to be opposite. So we've done experiments to measure and they're correlated. They're all separate. So then what they did was saying, okay, let's put them so far apart that when you measure the spin of this one, there's no way light could get to that one before you measured it. You measured it first. And we find out they're always opposite. And so we say these two photons are entangled now from when they were created. And it's not that their position was set that I'm going to be this way, you're going to be that way. It's got to be all directions possible until you measure. And then that one's opposite. It's always going to be opposite. So it's like they're connected. It's like if this one's twisted to here, that one twists. Yeah. But through space and time. I think the Chinese have done this with a spacecraft and on Earth. So that distance, they could still see entanglement.
What does that mean? Like, what is that?
Well, that's what we're beginning to explore.
What does that order mean? Because there's order there.
Yeah, there's a lot of order there. Well, I like to look at it as if we go back to the Big Bang, everything was one, all the matter came out of energy. Is everything entangled? Are all particles, that make up atoms entangled, which means we're entangled or something.
Right, we're all the same. We're all one.
Yeah, we're all one. Yeah,
right.
So that's kind of interesting philosophical question. Physically, we turn to how we can use it, and it's going to be used for quantum, or has already been used in quantum encryption, so that there's ways of sending keys to things to entangled photons that other people wouldn't be able to read. And then you've got a key to decipher something to get your information out.
I can't even wrap my head around the practical applications of that. Would that require, obviously, programming? We're talking about for programming.
And usually some source to create the entangled particles. Right now, we've been using light most of the time. There are particles, I guess. If we could do electrons that physically travel in wires, that would be quite interesting to see if they could maintain their entanglement. Because if it interacts with something else, you lose the entanglement, to be honest. So
yeah.
But we don't know how information is transmitted faster than the speed of light.
Right.
And that's, to me, the biggest mystery in physics.
Do you, as far as the applications of it, do you think that AI, first, let me talk about AI, because AI's played a big role in the artistic and creative space more than any other space, I would argue, today so far. So where does AI fit in its role in physics, space exploration today? And how is it used? Because I don't know how it's used in today's world.
Okay, so do you know there's two types of AI? There's AI, and then there's AGI, which is general artificial intelligence.
Right, like sentience, as far as we understand.
Approaching that.
Right, approaching sentience.
And so we're still just with AI.
Right.
And basically, we're looking at large data sets and pulling out from them what is asked or looking for similarity. And then we can assemble it according to the prescription you give, which if you've used anything, you have to be very specific.
Right.
And so it's not thinking at all, you wouldn't even call it intelligence, because it can do sort of one task very well, very fast. And that's the advantage to it. Now I actually get aggravated because if you do a Google search for something, it'll come up and start giving you AI stuff.
Right.
And it's reading and it's just putting things together.
Right.
A lot of times they're not connected.
Not accurate. Right. Yeah. Right. So a lot of it, because it's a language learning model, it's based off of what the prompt that you give it.
Right.
So unless you are, even if you're extremely specific, the results you get may not be accurate.
Right. Right.
So it's doesn't seem very practical in that sense right now in the realm you're in.
Right.
Right.
Well, it is in another way. We do have things, neural networks, which are a form of AI, and they actually learn from having data sets that they can review or home in their calculations on. There's been big battles, by the way, of using your data, your personal data, that Google would or Microsoft would glean from where you go in your websites and things like this. So that's used in training for AI and these neural networks that are behind it. And so there it's again learning how to do a task better and better. And that's used in physics a lot now.
Yeah.
I mean, a real lot. And one of the reasons it's also used is because we have so much data that it's impossible for humans to comb through all the data, to examine, to search for particulars that they're interested in their research.
Right.
So we do, in a real sense, data mining, where we have programs that can look for some specific things and other things, correlate them as well. So it's not a simplistic approach to it. It can be fairly complicated. And that's really where physical sciences are headed. At least, I would say they're headed that way. Probably biological as well.
AI currently, though, is, the most advanced AI that we know of, which I guess is OpenAI. Maybe. There's others out there now. But it's based on the language learning model.
Right.
So do you think that the language learning model is where artificial general AGI is going to head us, is going to lead us towards?
No, I think it's got to be something else.
Right.
And I think we just use the language model because that's how we communicate.
Right,
language.
Exactly.
So it's going to have to be more mathematical. The algorithms are going to have to not depend always on these data sets, but almost start to think for itself is, I guess, what I want to say.
Well, and that's the question is, even for me with the language model, there's no way I can wrap my head around it. No matter how much it learns, it's just a function of the program. And I don't think and I think a lot of people in that same community are coming to terms with this, that it's not just going to a flip's going to switch one day and it's going to be like, oh, I'm a computer. Right. So I think the means do have to be different for that to happen. But do you think that AGI will AGI be, is the definition of what we say AGI is, which is artificial general intelligence, is that it's understanding of its own consciousness? And what is that? Is that when you just amass enough knowledge to know that you exist? Is that technically AGI, or is that just that it knows that it exists? Because you could talk to a learning language model that say it exists today, right? But is that just what it's learned from the model?
Yeah.
And last one, is that any different from what we say? When we say we exist, is that just as as crazy and far-fetched as when an AI says, or a language model says it exists?
Yeah, I wouldn't say that it's realizing it exists. I would say that it exists on its own. Okay, and I want to explain that. So I always have to go to examples when I think of things. So let's look at an AGI model, and you want to mine iron because you're in the steel building enterprise, and so you want iron. So you actually make an algorithm to search out where iron is on Earth. You have it be able to control automated machines that will dig and basically create their own mines, M-I-N-E-S, not D-S, mines. And so it becomes a self-sustaining operation. So it knows that, okay, this digger needs to be replaced. So it's making general decisions that impact what it's searching for. Okay. And I wouldn't say it knows it exists, but it has another danger. I mean, it exists, yes, and it's existing for a purpose, but I don't think it's aware of what it's doing. However, even at that stage, it could say, okay, my goal is to produce a lot of iron and do it very efficiently. And so it's looking, and then it finds out that, there's a lot of iron in the core of the earth. So it starts digging a mine down and down. Does it care what happens? No. Does it care about humans around? No.
Right.
So in a sense, it's just become, even though it's general, because it has all these components that are doing different things, it's so singular yet in purpose.
Right.
That I don't think we can say it knows it exists, because in order to know you exist, you have to know that others exist outside of you. And I don't think it does that. So
yeah. And so in the sci-fi realm, in the movies where the aliens, take over, the AI take over, and in a real world sense, it would be more along the lines of disregard for humanity, not because it despises humans or think that, we've done so much wrong. It's going to be more along the lines of it's inefficient and it doesn't match with what my singular goal is.
Right. That's what I think it would be.
Yeah.
And I think, and there's a danger there. But turning on us, like I couldn't see it taking over all the nuclear weapons and shooting them off at each country, create a world that
that's Terminator 2 right there.
Yeah,
that's like my favorite movie.
Yeah. So,
are there any exciting space missions currently planned that you're aware of for the next decade or for the next while that you know of?
Yeah, there's actually one from the European Space Agency that's headed to Europa. And there's another one from NASA that'll be going to Europa. Europa is exciting because we know there's an ocean underneath it. And
Europa is another planet or star?
No,
or what is it?
Europa is a moon of Jupiter. And so we know that. And there's also Enceladus and Saturn is another example where we're pretty convinced that there's an ocean under that ice. So the object is going to be, I think the European one is meant to land and then maybe to drill into the ice and actually to see if we could get any water or see what's in the ice, at least if there's any organic compounds or something indicative of life.
Right.
So I think that's a very exciting one there. Farther reached ones. I know Tess has been looking at measurements of light from fairly nearby stars. Kepler looked pretty much farther, but fairly near to search for exoplanets. And it's succeeding very, very well. The big excitement around that area will be using the James Webb telescope. We are getting to be able to measure the atmosphere of some of these planets around other stars.
And these are planets that we feel could potentially have life or could...
Yeah, that's
could,
what we're looking for.
Right.
Yeah. And so Kepler was looking at sort of Earth, sun-like stars in a very far distance. The TESS is much closer, and they're also looking at a little slightly cooler stars in general, I would say. And so we're finding more and more planets. We're finding multiple planets around systems. And now we're actually getting fairly good to be able to recognize some of the major components in the atmosphere. So if we see carbon dioxide, that's going to be a big indication that there's at least the kind of life we know.
Can we get
possibly?
Can the results be pretty accurate, like the percentage of each thing, or is it?
Yeah, there'll be uncertainties that they have to give for it. Yeah. So, and I don't know how accurate they're going to be yet, but it's a really hard. It's using something called spectroscopy, and spectroscopy is wonderful. Tells us what elements are present in the sun or any star, but it's hard to do because you need light coming from the object, but you also have to pass that light through a tiny slit, and so you're diminishing the amount of light. And when it's from usually we look at the light going through the atmosphere of an exoplanet when it's transiting going in front of the star, so we can see the sunlight illuminating the atmosphere, and then we can pull out what the effect of the star is and just look at the atmosphere. But that is so faint, and you're taking it so. I admire people who can do spectroscopy.
And just so anybody who's watching, because we've already talked about exoplanets, but it's basically a planet that's orbiting around a star.
Yeah,
essentially, and
star,
that's not in our solar system,
right?
Basically, how far away and we were talking about Mars at the beginning. I think that like Mars is obviously the first step, because it's like it's going to give us the practical ways to get to another planet, right, and travel there efficiently and build structures there, et cetera. And through that, there'll be a lot of innovation and growth if there's money for it, especially, if there's certain ore and certain, gold and minerals or whatever on that planet that'll help drive the desire to increase innovation, which will hopefully that innovation will help us, increase our technology and be able to head to large or farther planets, exoplanets to terraform or not terraform. I guess if they're like just like our Earth, essentially, you would be terraforming a planet that's basically like the Earth, right? You would just be building, I guess. But how far off are we, do you think, from being able to, one, figure out what is on the planet that we're looking at, these exoplanets, and confidently say, okay, this planet is like Earth 2.0?
I'd say we're right there. I think we can. It's the finding of the Earth-like planets, but I think we can identify them very, very well now.
And then the next hard part, obviously, is the travel.
Yeah,
that's going to be the. Yeah. And do you feel like that? That's the limitation in a sense. Would you say that's the biggest limitation currently?
Yeah. So two things, but I want to say one thing because you said the next big step is to go to Mars. I actually think it's going to go to the moon. We're going to have moon bases, and fairly soon. The Chinese, I think, are going to probably be the first to have them. And then, but we'll also have to set up before that space station around the moon. So I think we're going to see happen in the next 5 to 8 years, maybe. And then Mars is we can go visit it, but I think that's going to be the practice run, doing that on the moon, and then we could head to Mars. So getting back to your question of which was
how far away we are from being, or is the travel to these exoplanets the limiting factor?
Definitely.
Yeah.
Okay. There are several ideas, which are all based on physics. The one way to travel to these is a multi-generational spacecraft, where basically you can grow your own food. You have going to spend hundreds of years maybe to get to the planet, and probably have an ion drive, which is a reality. Ion drive, just instead of propelling gases out, propels ions of some element. And just by Newton's third law, you push it that way, you go that way. But they're really small, so you don't get much of an acceleration, but you just keep them on all the time.
Right.
And you can start getting faster and faster. So we've had a lot of success with ion engines. Actually, there's some probes that are ion drive. And so it works.
And the longer it's dispensing, or the ions, the faster it's going to get.
Right.
Up to what speed?
Well, we could go actually theoretically near the speed of light if we had a long enough time. So, right. I mean, this is a great thing. Now, the the time it would take from current ion drive to speed of light would be probably thousands of years, I'd say. I don't know. I haven't done a calculation.
Mm-hmm.
But the multi-generational could use an ion drive when you get there. And that would be and we're going to get there. This is a really big spacecraft, so it's going to be hard to move. There's a lot of inertia mass. So to get it to accelerate, it's going to be a little harder if it's than a smaller probe.
Mm-hmm.
But that's one way.
It's got to be kind of sad.
Yeah.
To be a kid growing up on that, having your loved ones, knowing that you're not going to reach the destination.
Yeah.
know?
Yeah. Yeah. And then a better scenario would be where we have something where we can travel near the speed of light and get there very quickly as a consequence. And so there's...
Sorry, can I interrupt? I just want to talk about the multi-generation when you travel. When you think about where we were, I watched 1883 on Paramount. It's a show about the westward expansion, and how you'd be risking life and limb to go from like Texas to like Montana, and how the travel would take almost an entire year, and it'd be grueling, and a lot of people wouldn't make it out alive. And when you compare that now to travel, taking a plane ride for a couple hours and being there, and knowing that was just 150 years ago is pretty crazy to think about. Yeah. And so people, I want people to wrap their heads around that idea, because it would be it could be a multi-generational thing to be traveling, and then to be setting your roots somewhere somewhere not that far away on Earth. So when we're talking about doing the same thing on another planet, it's not that far-fetched, and it's not that far away when you think about how long ago 1883 was.
Yeah. So
I want to put that in people's heads, but keep going about the
but also, one thing, luckily for settlers, they were able to live off the land. In space, we can't do that.
Right.
That's why we have to have things with us. We won't be able to stop off on a planet or anything along the way.
Right.
So it's a harder. And then although hopefully there's not aliens that are going to attack you in space.
Space pirates?
Yeah. But you have other dangers, which is this radiation. And so you'd have to have the insulation for that as well. So it's fraught with danger as well. But, as you said, 150 some years, we look at how far we've come, we may be able to do that.
Right.
150 years.
Right. I know.
That'd be exciting. But I like you said, I want to be there.
I know. Part of me, when I think about where we were 150 years ago and where we are today, I just only wish I could somehow find a way to project into the future, just to see, just to know where it was. Because nobody, somebody who, say, passed away in 1920 or 1900 couldn't wrap their head around what's happening now, with the phones and the technology that we have. It's insane. So where we are, or, electricity, put Mozart here and sitting down and having to play the piano, and then you turn on the lights, they freak out at these bulbs. Things like that are just so beyond our understanding. So yeah, definitely wish we could find a way to extend lives, if only just to find out where we're going to be, that curiosity.
Yeah.
So sorry, go ahead. The second option.
Yeah. So there's more futuristic, which take the path of Star Trek. And we can't do it yet, but we think it would work if we could do it, and that's creating a warp bubble around a spacecraft. And Akubar and others have shown that this is not forbidden by general relativity. And in doing so, you would be like at rest, and you're squeezing space and time in front of you and extending it behind you. And so that is like a wave that pushes you ahead, if you want to think of it. But you get to travel great distances very, very rapidly. I mean, and you know, in Star Trek, they have warp, and warp is like the speed of light cube to that power or something. And so you could get very fantastic speeds this way relative to someone just at rest in the galaxy. Mm-hmm. But to you, it's not going to take you long at all. So
would this be going at the speed of light, or would this be?
No, well, in general relativity, you have to be careful because you have to talk about according to whom. Is it going to be a local reference or not? Mm-hmm. And you locally do not exceed the speed of light.
Right.
But
outside your bubble.
Outside, yeah, you would be.
Going at the speed of light. It is even traveling at the speed of light, if it takes, you know, how many light years is the nearest exoplanet or the cluster of exoplanets that you've talked about?
Well, we're saying actually there's some that are maybe 50, 100 light years.
50, 100, which is, I mean, relatively speaking, very, very little, but still 50, 100 years is a good amount of time. Is there a way to exceed the speed of light?
Well, that's what this method would be doing.
Okay.
So you would exceed, according to this non-co-moving frame, but in your frame, you're not exceeding it, so you're not breaking any laws of physics. So it would be okay. The problem is we don't have the energy to do this. I mean, this is that civilization 2 level we mentioned. So we don't have that, and but
we don't know how to harness it, or we don't, and we don't have it. Period.
We don't have it.
But
we don't have it. We don't know how to. Well, I guess we should say we don't know how to harness it. Yeah, that'd probably be a better answer.
Right.
And then the third way is one that I like, and if you ever were a fan of Stargate or Stargate SG-1.
The first movie I saw,
yeah.
That's great, yeah.
And so this is literally creating wormholes. So wormholes are going to be connections in space and time from one to another that if you go through, you travel like that, and you can travel millions of light years through this wormhole because of how space and time can be melded. To do it, though, we know how to do it. I mean, we actually do know how to do this.
Oh, really? Wow.
Yeah, but we can't because you have to create a wormhole that's stable, and we can't do that yet. Supposedly there's some particles we haven't discovered yet called verterons to hold it open because it wants to collapse right away, but to hold it open. And then you have to have one which is large enough that, you know, you could pass through at least in machinery, and that starts to take super amounts of energy. So we're not there yet.
And what you would just plot a point, say, I need to be 1,000 light years in that direction, essentially, and the wormhole would open on the other side, essentially?
Well, yeah, we don't know how to do that. But see, the thing with wormholes is you can have a beginning and an end, and you want to know where it is. You just don't want to let it go and open anywhere. Mm-hmm. And so that means you've had to have been there to have something there to mark that and connect to it.
I see.
And so that's going to be a, level 2 civilization or more, maybe level 3, where they can go all through their galaxy. And
have you seen Event Horizon?
Yes.
I'm would want to what they travel through to this dimension, this hellish dimension, and I'm like, man, that's kind of a scary thought.
Yeah. But this is a way to travel in space. And I like the wormhole idea. I like the warp bubble idea as well. I think we might see 1 or 2 of those eventually come about in 100 years. Things are moving pretty quickly.
Right. Yeah. That's crazy. Yeah.
I'd like to give you one other
for sure
comparison that I find instructive, and that is if you were to get in a spacecraft and constantly accelerate at 9.8 meters per second. So it'd be, things would fall to the back of your spacecraft like they fall on Earth. So you'd think you're at home on Earth. And do that say for 2.5 years, decelerate 2.5 years, okay, and then turn around and come back the same way. So it's very realistic. It's not that, bam, you're moving super fast.
Right.
You just have to accelerate to it. So this is like using this ion drive, but a really powerful ion drive. You've been gone, according to your life, 10 years.
Right.
So when you came back, you would find out that the calendars on Earth were 2 years ahead. So you've gone into the future of the Earth. Can't go back, though. So
7 years would have passed for everybody else on Earth.
No.
Sorry.
10 years for you and 12
years for everybody else. Okay.
Yeah.
Right. Why is that? I saw it in Interstellar too, but how does that work?
This is relativity, and relativity. There's two. This is special relativity. Special relativity says if you travel fast enough, you go far enough, and you come back, and it's the coming back, you can go into the future. So fast, so that you can see it happen. So that's why I said, we're got this constant acceleration. And then the key idea is that as you're traveling, you should look at the Earth and say, oh, it looks like things are aging on Earth just as they're aging here. Everything should be symmetric. But you're the one who turns around. And that turning around in physics as you jump inertial reference frames, it means that you've broken the symmetry. And now you will be the one that experiences less aging than those on Earth. If we carry this scenario out to, let's say you can travel 60 years of your lifetime by this method. So you go 30 years out, 30 years coming back, but you have to accelerate, decelerate, You could travel to the edge of the galaxy. No problem. When you got back, the Earth would be 1.1 million years older than you. So you have jumped into the future. And as I said, you can't go back. There's no going back.
I'm having a hard time grasping this concept. Can you dumb it down a shade for me?
well, okay. It's that, okay, let's do this. Suppose on Earth, there's a signal going up. It'll be light, like blip, 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 blip. And you would be watching this as you go, and you'd get a blip and a blip and a blip, And yeah, you're getting farther away, but the timing and the blip should be the same. And they would say your blip timing is the same as well. When you turn around and come back, as you turn around, come back, all of a sudden all these blips are going to start adding up and much faster and much faster. And then you're headed back. And that means the number of blips is kind of time. And you're going to see a much greater time having gone by on the Earth.
Why is that?
Well, we can't say it's the way special relativity works, right, because time is relative, but we can't give a more mechanistic answer for that.
I see.
Yeah.
Okay.
The other way of doing this as an interstellar is to actually bend space-time with massive objects like a black hole or something. Mm-hmm. And that can do the same thing of stretching time. Which, by the way, I'll give you, this example might be a little easier to understand. It's a black hole, event horizon, you mentioned the movie. So event horizon in a black hole means that if you're inside that, you can't escape. Gravity's too strong. So gravity's like a well. If you imagine a well going down, and it's so steep that light can't even escape out of it. Light just doesn't have the speed to climb up it. So that event horizon demarks the inside and outside of the black hole.
The point at which just light can't get out.
Right.
Okay.
So now if you were to watch some probe or let's say astronaut get close to the event horizon, you're very far away. Mm-hmm. You see that what's happening in that curvature space-time, that well, is that time slows down for that person. Or your observed time of that person is much slower. Mm-hmm. So you would see the person like barely moving. and literally would hang just on this side of the event horizon forever. But to the person, the astronaut, life is normal. You get there, you get gravity, you get sucked in. And you also get spaghetti-tized because you get stretched by the extreme change in gravity from your head to your toes. And so you fall into it. But we don't actually see somebody fall in. We see them there. And then light, as it's traveling to, is also shifted. And so it's not visible anymore. It moves into infrared and microwave and radio waves. And so it vanish, but it's, according to our understanding, still out there.
Right.
Now, something can come and knock it in or something like that. But I'm saying if you just put it right at that and we're kind of stable there for a while, it would still hang there.
And you mentioned, I mean, obviously that would kill somebody to spaghettify them,
Yeah.
right? But you mentioned in Interstellar they used the warping of space-time with massive objects like a black hole.
That was a black hole.
So essentially, how would you be able to travel? Would that allow? That's not necessarily a wormhole. That just allows them to travel faster. Is that what it is?
Yeah, kind of. Yeah, I guess you could say that. And that's how he was able to himself go into the future, where he sees his daughter really old, and he's had that kind of same effect as going off, coming back, but a more localized version with taking advantage of the curvature of space-time.
How is that way? How do you explain that as far as the time travel relative from one person to the other? It's still special relativity.
Yeah,
It's
that's
the same.
special, and this is general relativity.
I gotcha.
Yeah. And general relativity deals with accelerated frames of reference.
Sorry, when you say this, Interstellar is general relativity.
Yes.
So how would that work? I haven't seen the movie in a long time, but how did he age slower than?
Well, he went like really close to the black hole, and that's when things got weird too, because that whole bookcase thing and stuff like that. And
but even earlier in the movie, when they were traveling to the planets, he's looks the same, but he's talking to his daughter, and she's already grown up.
yeah, well, that's also because of the black hole presence, because it's that black hole that they were using to get to these other worlds, and so I think it's also gravitational effects, which means it can stretch space and time.
I get this stretching of space.
Stretching of
you,
time.
You explained it to me well last time. You're basically, it's like, imagine like a black sheet and
Yeah.
then like putting a marble on it or a ball on
Yeah.
it. You'll see that the rift of
Yeah.
it is if the object is massive enough, right? But what about the time?
You just have to think in 4 dimensions.
Got it. Done.
That's the hard part. I mean, but time does the same kind of thing with the bending from the way time is affected too. And that's the connection of space and time being interwoven into one was, one of the.
Oh, so if you bend the space, time bends with it.
Yeah.
They are, because they are directly correlated.
Yeah. Correlated, related, interchangeable. Yeah.
Then if space bends, time bends.
Yeah.
Essentially. Okay. All right. That makes sense. A little bit, but more sense than before. So I want to kind of go off on a kind of a fun one. I'm fascinated with conspiracy theories, and so I'm going to list off a few different ones related to space, and I want you to give your input on either their plausibility or debunk them, right? With your knowledge. So the first one, the big one, is the moon landing hoax, right? That the moon landing was faked by NASA, and some alleging that it was staged on a Hollywood set. And so theorists point to pieces of evidence such as anomalies in the footage, the lack of stars in the photos, the strange shadows on the moon's surface. And this is one of the longest running space conspiracies. But I mean, we see the moon, we know that it's there, but do you have any thoughts on that?
I don't believe in the conspiracy theory for that. The reason is, first of all, the astronauts who went there, I think, were profoundly affected by the trip and seeing the Earth. And I think some of them have talked about it. Neil Armstrong was pretty quiet about everything in his life, but I think they, by and all, were really affected by it. And to me, that says something real happened. It wasn't just on a Hollywood stage.
Right.
The other thing, I've looked at reflections in their visors and things. I think it can all be explained through physics, and I don't think it had to be a Hollywood set. The stars, not seeing it, you would see a blackish if you look at it, but the stars are
still far away.
Yeah, still far away, and you still got that sun because they do have to have some light. So I imagine if they went on the far side of the moon, you would see lots of stars like we see.
Oh, right. Just like when we were out in the stars the other day, the reflection of any kind of light pollution is enough to make stars almost impossible to see.
Yeah.
Right.
So I don't find any credibility in that.
Here's the big one: flat Earth theory. So that's a fun one. I mean, I'm sure it's been debunked 1,000 times, but in your own words, debunk that one for us.
Well, I just have to go to modern technology, and that we have orbiting space stations and other things, and we do see a full view of the Earth. So I don't think it has flat or an edge. So I'd have to say it's really a 20th and 21st century proof that it can't be flat. It has to be a three-dimensional object.
Right. I mean, just knowing that, going out on the telescope a couple of nights ago, just seeing Saturn being perfectly round, seeing the moon. Why would the Earth be any different? Why would there be a flat entity on the Earth?
Right.
And I said this to you before we started, but seeing a planet through a telescope is just amazing. Your first time seeing it, just like you explained to me your first time, but it's just, when you see it not through a photo, but when you see it with your own eyes through a telescope, it's just mind-blowing, because then you truly get a sense of the vastness of space, and kind of gives you a sense of where you are. It makes you feel very small.
Yeah.
When I watched that. Are you familiar with the secret space programs? Governments around the world in the U.S. are running advanced secret space programs that the public's unaware of. That's pretty broad, but people believe the programs involve advanced spacecraft, human colonies on other planets or moons, and even contact with extraterrestrial beings. Do you think there's any of that going on?
If I'd answered the question with my knowledge, I'd have to kill you. No, I don't think. I don't know of anything, and physicists, we always like to go to physical explanations for things.
Sure.
And so I wouldn't discount things. I know one is that there's aliens living under the Earth and stuff like this.
Mm-hmm.
I'm not going to discount anything. I have to have more evidence,
right?
And have it subject to at least more observation, if not measurement.
Yeah. Like last time you spoke about your theory for the unidentified, objects that a lot of these pilots have been seeing, UAPs. You'd mentioned lights being emitted from submarines. Right. So that's the kind of technology that could be present and not well known by anybody in the scientific who isn't involved in the military.
Right.
That could be used to explain that phenomena, for example.
Yeah.
Which I have in another video that we did. What about Nibiru Planet X? A hidden planet called Nibiru or Planet X is on a collision course with Earth, which will cause catastrophic events.
Okay. No, I don't think so. There used to be a lot of thought that there was an anti-Earth on the other side of the sun, so we never get to see it. Likewise, we know that it's definitely not there because we have satellites that have gone around the sun or do orbit the sun, and we see nothing. There's also a 10th planet that people think is out there, fairly large, and this is all by how it's disturbing things in this Kuiper belt, and there's not solid evidence for that yet even. So I don't think there's a planet on a course to crash with us. And as we discussed earlier with asteroids, we would probably know about it because the planet's fairly big. In our solar system, we could probably observe that fairly easily.
All right, next we have the Black Knight satellite. There's an ancient alien satellite orbiting Earth and has been monitoring humanity for thousands of years. Known as the Black Knight, this supposed satellite has been linked to alien origins. Conspiracy theorists claim NASA is aware of it, but keeping its existence secret. Have you heard of this one before?
No, I never did. But, I mean, it could be plausible. I mean, if you don't have any observations of it or any data on it, then we don't know anything about it except that it's a theoretical construct.
Right.
But so I couldn't discount that. Entirely.
Unless there's proof for it. So many movies have used the explanation of our advances in technologies because of alien life, Transformers, aliens, and what's the 2001 Space Odyssey, so it's cool to think about that idea. But yeah, unless there's physical proof for it, it's hard to say one way or another. So.
And maybe they're putting those sort of obelisks, those shiny obelisks around the Earth that appear out of anywhere.
That's right.
Which then you go to why. There's always got to be a why.
What about, and I've seen a lot more of this on the media and people talking about it randomly, but chemtrails, and I don't know how much of this is conspiracy or fact, but about high altitude spraying by airplanes that extends, really high up. To part of a geoengineering. Well, some people say for geoengineering or mind control operations, but what about just the more on the side of like HARP using it to control the weather?
We do know that all the jet contrails affect the atmosphere. So
what does that mean? Affect the atmosphere?
That it can cause, because it's depositing some chemicals in there. So it affects the balance of chemicals in that region when they go by. And so you're in a small way changing concentrations. So there can be some effects of, and I don't remember what the contrails are usually. I mean, it's water vapor usually, but there are some other things in there, and that actually can increase global warming. So there's a connection there. So I think there is something there.
I'm reading. Are you familiar with HARP, the High Frequency Active Auroral Research Program?
A little bit.
Yeah, it's a research facility in Alaska designed to study the Earth's ionosphere, and it uses powerful radio waves to investigate ionospheric properties and enhance communication and surveillance technologies. So conspiracy theories have surrounded HARP, some claiming it's used for weather manipulation. But are we at a point to where we can manipulate the weather?
No.
Well,
we do.
But without control, without knowingly controlling it, right?
Yeah,
it's like the jets, the water coming out of our jets or whatever's coming out of the jets is affecting it, but we're not controlling it. We're just affecting it. Right.
I have a former student who got his PhD and he works at Los Alamos, and he's an expert in ionospheric physics. And there's a lot we know in studying the ionosphere that we can tell about explosions halfway around the world and many things people would never imagine that we know. Besides listening in to other countries, there's a lot that can be gleaned, especially when there's a disturbance in the atmosphere from something.
When you said explosions halfway across the world, what do you mean?
Well, like if North Korea were to have a nuclear bomb, say a small one, go off, we would know immediately from the ionosphere. We'd also have seismic waves too, so we know it in many ways. So, but this could be one that's, say, not land-based, but higher up in the altitude, in the atmosphere. We would know about it.
You would just we'd pick up the waves, the frequency or the energy,
Yeah. We'd pick out the disturbances in the ionosphere.
And why the ionosphere specifically than any other like stratosphere or?
It's just that's a nice conduction area
Okay.
for signals, and so as it has this concentration of ions, so things promulgate in there and become something we can measure.
I see. Okay, cool. How about this one? CERN and portals to other dimensions. So the Large Hadron Collider at CERN, which I've driven around because my family lives in Switzerland or Geneva, right on the border of France and Switzerland, actually. So we've driven right around where they're studying. It's been cool. It's cool. But CERN is being used to open portals to other dimensions and even summon dark entities.
Yes. Okay, it is a way to open portals, I would agree, because you're pumping a lot of energy into a small space, and that has a great energy density. That's kind of what we need to open those wormholes I mentioned earlier. But no, it's these are proton beams. I mean, they're tiny, and so nothing for portals into other dimensions that we can understand.
And the purpose of everything going on at CERN is to, at first, or once I heard it, to discover the God particle, which would explain.
It's already been discovered.
It has been discovered. Okay.
Yeah.
And that basically, does that help back up the Big Bang Theory, or what is that?
Yeah. Well, it goes in something called, there's a standard model in cosmology for the Big Bang. There's also a standard model in particle physics, which describes the types of particles and how more complex things are built out of quarks, which are like the fundamental particles. And so CERN definitely helps our understanding in those areas. It's also used for searching for this dark matter that we don't know what it is.
Have quarks been established as actual?
Oh, yeah.
For
everyone, I wouldn't say everyone believes in quarks.
Okay.
I did my thesis in graduate school on a quark, the strange quark at that time, and calculated its upper limit to its mass. And so, yeah, everybody uses quarks as pretty much the standard model that we know how they're interacting.
Very cool. And so if any place currently is going to discover ways to manipulate wormholes, or would CERN, is CERN where it's being done?
Probably, yes.
Aliens built the pyramids as stargates. Pyramids, particularly those in Egypt, were constructed by extraterrestrials as stargates. I don't think I've done research, and we still don't know how pyramids were built, from my understanding. We still aren't sure how it was done.
Well, a recent idea that I read that I liked was that there used to be like canals next to them. There used to be water. And so they figured out how to float on logs, big blocks, down from where the quarry was. And then, they have slave labor and ropes, and I'm sure they knew pulleys. And so I think it's more reasonable that they could have built it.
I agree with you on that one. But this theory merges with ancient astronaut beliefs with space travel, suggesting that advanced beings use pyramids as a form of technology to access distant parts of the universe, which goes cool with the movie.
Yeah, it goes with the movie.
Yeah. But then again, if you don't see it, yeah, I mean, that's great. Awesome. Thanks for indulging me on those. All right. Well, thanks so much for coming today.
Oh, thank you.
I really appreciate it. This
is
is
a lot
great.
of fun. Yeah, enjoy it.
See you soon, hopefully. Yeah.
Okay.